In a world where space and time are intertwined, one man dared to challenge the status quo. His name? Dayton Miller. His weapon of choice? A flute. But not just any flute. This instrument held the power to unleash the ether, a pervasive medium once thought to fill the universe. Miller, a physicist by trade, a musician at heart, discovered a harmonic resonance within the ether. He found that his flute, when played with precision, could manipulate this elusive medium. His melodies, a symphony of science, had the potential to shift the very fabric of reality. However, a sinister force lurked in the shadows. The Einsteinian demons. These creatures thrived in the distortion of space-time, causing chaos and disruption. The world needed a hero, and Miller was ready to answer the call. With his flute in hand, Miller played a tune that echoed through the cosmos.
All right, hello and welcome to our annual recap of the celestial theodolite. I'm going to give a quick recap and update on the new measurements. And then if anyone has any points of contention, we'll go over a couple of points of contention. And then if anyone has any new points or questions or whatever questions, but this will most likely be a short one. Okay, so the basic premises here, using basic planar trigonometry, we're going to take the arctan and use the difference in altitude between the observer and the peak of this mountain over the distance to get an angle. That's going to come out to be 2 degrees and 31 arc minutes for the example of Pikes Peak when you are 50.7 kilometers away. And then to get the globular prediction, we're going to use the arc sine, which is the distance over the radius, which looks like this. That's going to give us 27 arc minutes. So we're going to subtract 27 arc minutes from our prediction, which takes us down to about 204 or 2 degrees and 4 arc minutes for the raw globe prediction. And then we would add celestial refraction to put us up to 219.
206. 219, yeah.
219. And of course, if you do the 2 pi method to get the angle here, you would end up using terrestrial refraction. Your calculation would be 2 degrees and 17 arc minutes raw, and then you would add 2 degrees for terrestrial refraction. So either way you slice it, you come up with a deficit here. There's 2 different predictions for the calculations. One comes out to be 2 degrees and 19 arc minutes total for the globe. So meaning the physical elevation of this peak in reference to someone that is 50.7 kilometers away will have an angle of 2 degrees and 19 arc minutes. And then on a flat Earth, for someone that is 50.7 kilometers away, their angle will be 2 degrees and 31 arc minutes for the raw physical elevation of that peak. Now, what we're going to use now is stellarium in reference from the peak of this mountain, using this same angular relationship of 2 degrees and 31 arc minutes. We're going to look up from this peak at 2 degrees and 31 arc minutes, and we're going to see what stars intersect and what times they intersect with that point in the sky. And then we're going to wait on the ground and look at this mountain, and we're going to see if any stars get occluded at the time that corresponds with 2 degrees and 31 arc minutes in the sky versus 2 degrees and 19 arc minutes in the sky. So basically what we're doing here is we're not making an optical measurement with a theodolite, because if we make a measurement during the day or even during the night, excuse me, you're going to measure it to be about, 2 degrees and about 19 arc minutes from that distance using modern theodolites. So in our point of contention is that the visual field and the spatial field are different from one another, and the spatial field being Euclidean and not actually curved in any way. So this is going to be a test of that separation based off of timing when the star gets occluded. All right, so when we go into stellarium and we play out different nights or different times of night through different nights, we find some stars that intersect at these corresponding times. We'll just go over the Pikes Peak ones real quick. A couple of the highlights. What we're looking for is these degrees right here to be same, and then we go out and see if the time that star is physically there, because what we're doing here is we're referencing stellarium with refraction turned off, so it's just referencing the nautical almanac true position of the star, not the apparent visible position or refracted, anything like that, right? We're just going off the supposed true geometric position of the star at that time and the angle it is with respect to an observer on the peak of the mountain, looking up at 2 degrees and 31 arc minutes. Now, we have not told stellarium that we are observing from this far away or anything like that. And what we're going to do now, play a couple of videos. Second. So yeah, we'll watch a star get occluded. So this is what we're looking for here. Stars to get blocked by this mountain. So when we no longer see the star, right, this is the time we would write down from our recording device that is synced to GPS time so that we know when that star is no longer visible. And if that time corresponds to 2 degrees and 31 arc minutes, then that means that the Earth is flat. Because the only way that that geometry could be completed is if it's planar. All right.
Yep.
So let's see here. I think that pretty much covered everything I wanted to talk about in the beginning there. Give me one second. Okay. So there was a recent argument put forward. About tangents and refraction on the other side with respect to Mike's house. Now, keep in mind, the only part of this that we're concerned about is what's happening on this side of the diagram. The time that corresponds to 2 degrees and 31 arc minutes is the only time that's being measured. So let that sink in a couple of minutes, because 1 arc minute translates to 4 seconds in timing. So if the prediction is of a difference of 11 arc minutes, there's going to be 44 seconds in timing difference when the star isn't visible. The only timing that has ever been measured are ones that correspond to the flat Earth timing.
Yep.
All
It
right.
would be a huge timing difference.
There was, let's see if I have I don't have the other ones. But there was, what was the other one? What was it? Doing the observation from 1 mile away using something that's
That was
200
John,
meters tall.
a
Right.
small hill.
So
Yeah.
the difference in that would be, the difference in elevation there would be 8 inches. And the timing difference isn't going to be, I don't think that's going to be you're not going to be able to distinguish it. Like with this, we have an 11-second timing difference. So let's say you don't see the star and you want to add like 2-second plus or minus for your air margin, right? So you add 2 extra seconds, right? So we still have a window where we can, where it's still super distinguishable between the two. So using a measurement where the discrepancy is going to be 8 seconds, what's that going to translate to in timing? I mean, that's in the verses like when you can't see it, and like that's going to be not a proper usage of the apparatus.
Isn't the point of using a farther distance away from the peak to accentuate the difference between a globe timing, like occlusion timing versus a flat occlusion timing?
It's specifically the purpose, because if you think about it like this, the angular excess over an equilateral triangle of 1 kilometer is 0.002 arc second. That's not even a real thing. Like you like, okay,
There's
dude.
no way to make it mutually exclusive, but the farther away you put the observer from the peak, now you can make it mutually exclusive by checking the timing.
Yes, sir. And let's see, let's go over. So the most recent document here that was added from Heffron provides, actually, let me bring up, it's easier here. Have it somewhere.
Why would you want to make it why would you try and make it a small hill a mile away and not try to show the difference? It's so weird.
I have a question, if I may.
Yes, yes, sir, you may. Go ahead.
Okay, you said that you used tellurium and with the refraction turned off, right?
Mm-hmm.
So
Yes.
what kind of refraction are we assuming that was turned off?
Ooh, so the Stellarium uses a base 15 arc minute celestial refraction. So they just throw on 15 arc minutes. So so when you go to that mountain peak and you do 2 degrees 31 arc minutes with refraction off, then you add it, it puts it at 246 or something like that.
So there's a standard refraction and they're just removing it type deal.
Yep.
An arbitrary number based on the 50 degree.
Yeah, within that arbitrary number, they find the globe, though, right? All the time. That's the Michael's, I think, main point. That his main takeaway and realization was that doing this repeatedly was that the globe can only be found in that refractive correction. And if you
Which
look
what
at
made
chat,
him a flat earther.
I just put the two, the difference between the two for this observation.
Yeah, and real quick, one of the big things he pointed out on that, with the difference in refraction being made up, for the globe entirely by celestial refraction, when you do the arc sine of this and get the 2 degrees and 4 second prediction, the entire difference, like that 27 arc second offset, is entirely made up by adding refraction back twice to get what the globe predicts on the peak. Like, it literally only exists as a refraction correction.
You don't say.
Yeah, with respect to a flat baseline.
And real quick,
Allegedly.
and all the
Yeah,
other
go ahead.
globe examples they put forth would require a timing before ours, right? The timing and the
after.
corrections are after. Okay.
Yeah.
So it would all be after the actual occlusion. I mean, it would take more time for it to go through the supposed atmospheric opacity and Earth curve or whatever, as opposed to being right there.
Well, it has to get lower in the horizon because the peak is physically lower relative to the person that's using the peak to do the occluding. But yeah. So let's see here. There was a discrepancy here on Green Mountain. These two stars here are, what was it, about 15 arc seconds off or arc minutes off. So we'll have to check into that. There was a discrepancy that we found last week, but it ended up being daylight savings time. So I'm not sure what's going on with this one because this one doesn't fall under daylight savings time, but we could come back to these or whatever at another time.
Two
All right,
out of
all.
like
All
a
right.
lot of them.
All right, so does anyone have any questions, comments, or concerns? I know Jesse scheduled some time off for this, I heard. How you doing out there, young Jesse?
Indeed, sir, I did.
What's up?
The first two stars for Blodgett Peak are actually closer to the globe prediction than to the flat Earth prediction. Have you investigated that?
No, I have not. What's the timing difference you got for that?
I measured the difference in arc minutes. I didn't measure the timing distance or the timing error.
Wait, you're doing your own thing again?
Well, I mean, if the procedure
Well,
works, I should be able to
well,
use it.
Okay, well, 4 seconds is equivalent to 1 arc minute. So what's the
So how many
timing?
arc
What's
minutes?
the timing difference?
The difference in arc minutes is it's less than 4 arc minutes from the globe prediction and about 6 arc minutes from the flat Earth prediction.
So 2? 2 arc minute timing difference? Is that what you're saying?
I did not check to see what the timing difference was.
Well, if the difference is 2 arc minutes, then it's 8 seconds.
8 seconds, right?
So
But
did it get occluded at the globe time or the flat Earth time?
closer to the globe time.
Okay.
And if this can't reliably, if the method can't reliably differentiate between flat and globe, then what good is it, right?
Well, it's
Well, it just
great.
depends
It's
on the.
it's great. And 2, we're talking about possibly the limitation at the angle where it's at 1 degree, because the blood jet peak ones are where it's at 1 degree. And if when the timing difference is only 4 seconds, but you're saying, how could it be closer to the globe if it has to be occluded first by the flat Earth? It either gets occluded later or at the time that it matched.
You're gonna have to show that, Jesse.
Okay. Would you like me to share my screen?
Yeah. Or you send me a screenshot, I can pull it up or whatever.
Or it is the spreadsheet I shared with you on Telegram a few days ago.
I can bring it up.
So if you want to pull that up,
Yep.
then you can look at my formulas while you're at it.
I've seen them.
Yep, that's it.
Mhm.
So those 2 Blodgett peak ones right there,
Mm-hmm.
7 and or whatever those are.
Down
I
here.
can't quite read it. Well, so for some reason, when I put the time and the date and the location of the mountain peak into Stellarium, I got slightly different altitude angles than you did. So the ones down there are using the altitude angles reported in Dr. Heffron's spreadsheet, and then the one up near the top, or the pair up near the top for Blodgett Peak, are using the altitude angles that I got from Stellarium using your guys' date and time and location. So
What are you putting for the location? The peak, right?
Yeah, the coordinates are right there for a target location. I put Stellarium at the target location.
Yeah, he did it to the peak. He's got, otherwise it would, the Heffron angle would be off. He did it right. All right, so for Blodgett Peak, we got 1, 11, 11, and globe.
Yeah, so the Heffron method that I got from Stellarium was like, I think about 40 arc seconds roughly lower than year 2. But either way, they're both closer to globe prediction than flat Earth prediction.
Okay.
Were you when you're done with that, I do have another question on some other data points.
Go
Does
ahead.
that mean that every other single data point that you went through more correctly matches the flat Earth prediction, but these 2, when you did it, were 2 arc minutes off? Is that your position, Jesse?
I mean, it's fair.
Well, but if that 2 arc minutes off makes it closer to the globe, then how can you really say that it could be used to differentiate, right?
Well, statistical significance for one, but anyway.
Anyway, I also tried to sort out Green Mountain and Green Horn Mountain, and I couldn't even get sane values for those, and neither could Ruhif.
Greenhorn. Was that? Yeah, that was the one I covered.
That was the. Yeah.
Okay, so you'll get us
Yeah,
updates on that.
Yeah, I emailed him earlier.
Okay, what about Green Mountain?
That was the one I emailed him about.
Okay, what about Green Horn Mountain?
Wasn't aware that Greenhorn Mountain was anomalous. The one that you said was you only had 2 highlighted. It was the Green Mountain ones.
Oh, I highlighted every other pair because to save time, I just did the first 2 stars from each series. So that's just
Oh,
the
I see.
highlighted.
So you were sending them. I see. Okay. Yeah, my mistake. I misinterpreted that. I thought you were sending the 2 highlighted ones. So yeah, I'll ask him about that then.
Jesse, what do you have to say about all the other ones that have a significant difference between globe and flat Earth, where it matches mostly the flat Earth than the globe?
All the runs right around 30 miles. Well, if you were to plot a graph, which I did, comparing the difference between the Heffron method and the FE predicted versus distance, you'd find a negative error closer than about 30 miles, and then a positive error past 30 miles, and where that error line crosses around 30 miles, that's where they match. So it's basically where 2 lines cross. If the distance and altitude is correct, then it's close. Although sometimes it's closer to globe Earth, sometimes it's way below the one or way above both of them.
Didn't you just say it's only 2?
Yeah, but now he's trying to make the case that wildly inaccurate data, the whole thing is thrown out, obviously, because Jesse didn't do it right one time, so it's invalid, right? You got to keep up, Beast.
Oh, I'm just trying to understand his position. So 2 out of all of the other measurements you're saying are more closely to the globe. So my question was, what about the other 40 measurements? Like, what do you say about that? That are more, closely related to flat Earth.
I'm not sure what 40 measurements you're talking about. The spreadsheet that I'm aware of had like, let's see, 1, 2, 3, 4, 5, 6, 7 different mountain peaks. And I looked at the first 2 of each of those, except the Pikes Peak one. I did some random ones from it. But look at Shan Mountain ones. That one, that's on lines 7 and 8. That one is closer to the flat Earth prediction, but only slightly. It's almost in the middle. Well, in fact, the second star in the list is 5.7 from the globe and 5.73 from the globe and 5.77 from the flat Earth. So it's actually closer to the globe on the second one and closer to flat Earth on the first one. So again, it's like it's equidistant between the flat Earth and the globe Earth prediction.
No, but the timing would be different for one. It's either one or the other. It's all about when the timing happens. So if it doesn't match the globe with the timing occlusion, then it wouldn't have been occluded.
I'm not sure what you're saying. If the measurement is halfway between globe prediction and flat Earth prediction, how do you know which it's pointing to?
Halfway? What do you mean halfway?
Well, can you magnify there, Alan, on lines 7 and 8?
Which column?
AJ and AK. By the way, see that 100% in the top left corner of the screen? You can actually use that to make the font bigger too. Yeah, that one. Those. So you can see that first one is closer to flat Earth because it's 5.3 versus 6.2. The second one, though, is 5.73, which is less than 5.77. So on the second one, it actually is closer to the globe, just barely. They're both very, very nearly equidistant between the flat Earth and the globe Earth prediction. One's on one side of the line and one's on the other side of the line. See?
Josie, you said Pikes Peak. Do you live near Pikes Peak?
I couldn't understand that, Larry.
Do you live near Pikes Peak?
No, I do not.
Okay.
So Jesse, it's only one timing that matters, and that's when the star actually gets occluded.
Well, I'm not sure what your point is. I took the raw time, date, and target location, put them into Stellarium, just like it's claimed we can do. I set Stellarium at the peak of the claimed target, the indicated target, and that's the numbers I got. And I'm not sure what you want me to say. If the method works, cool. If it is not trustworthy, if it's not reliable, then what do we, it has to be consistent and reliable to be meaningful, right?
It's consistent and reliable. I don't know why you're saying it's not consistent and reliable. You're using the timing of when the star gets occluded by a peak of a mountain. It's pretty reliable. You're using a physical object to block the light of a star, so then that way you could take out the refraction argument between you and the mountain peak. So that's why it's reliable.
Well, he's basing it all on the just 2 arc minute discrepancy that he got from what Heffron put forward, right? And no one else has done that yet to get that similar discrepancy. We haven't done it to see if we got closer to his or to Jesse's, right? We haven't done any of that. He's just assuming that all of it's bunk now because that's what they really want to believe.
Well, and I know the Heffron formula too.
Okay.
Yeah.
Any other rebuttals or questions?
Well, yeah, I wanted to respond to that because, like, we were talking about last night, the pendulum, and this is a little bit off topic, but I'll come back around. And basically, I was like, okay, well, if it changes during the eclipse, like, then does that really measure Earth's movement? And then, you responded about like how, for the majority of the fact it's the same, but you're going to get discrepancies, and that's okay. And that'll happen in any experiment, is what you said. So I don't know. I think that we should just look at the overarching evidence, like what is gonna happen most of the time, because there are outliers in many experiments and stuff, but as you were saying last night, that doesn't mean to throw out all the data.
But
Thing
what if you
is,
really
those are
wanted?
tight. Like that's a 1 degree angle too. The ones that you're pointing out, that's pretty.
Yeah, through the hardest atmospheric opacity that there is, or whatever, to try and make an accurate observation to see if we get
pretty.
included.
Yeah. I mean,
So-
all that matters is when the timing happens,
And-
then the
an
globe
arc
has to
minute.
come up. Yeah, and the globe has to come up with a way to have the same timing occlusion, but it seems like, except for those 2 that I haven't really looked into yet, but the rest of the time, it's like it's going to be way off
So
if you're on a globe.
is there data for the rest of the 40 peaks available?
No, not peaks, just other stars,
Other observations. Using
other
those peaks,
observations. Yeah.
Oh, okay.
Yeah, there's.
which
let's
all
see,
match the
1,
flat Earth
2,
timing, by the
3,
way,
4,
Jesse, which I'm
5,
sure you
6,
agree
7,
with.
8, 9.
Well, what do you mean all of them? So you're saying that the first
14,
2
15,
that I picked for Cheyenne were vastly different from all the following ones for Cheyenne?
No, I have no idea. I've said no one's actually double checked your deviation from said, results. If we have only Heffron's results and Jesse's results, and you said, oh, these 2 are 2 minutes arc minute difference, that's all we have. We haven't been like, oh, well, when we replicate it, we get this, or when just like we did with the first observation, right? Everyone on their own replicated it. Everyone went into Stellarium. Everyone found their position. Everyone got within, 1 arc second or whatever to get it super close. We haven't done that with your so-called discrepancies. So, I mean, we definitely will now that you've brought them forth.
But it's 2 out of 39. So there's 37 other observations that you have to address, Jesse. What do you say about those? That was my question earlier.
Well, no, it looked to me like the each group was pretty consistent. So I don't think if I looked at the rest of the Blodgett Peak ones, they would be significantly different, or the rest of the Mount Rosa, or whatever. I think it looked like the grouping was pretty good. But if you would like to take me later with the an equal number, 7 more that match all match the from the Blodgett, Cheyenne, and that match.
So you're
closer.
not. So you're not saying that those Blodgett peak discrepancies, those two that you're mentioning, you're not saying that there's something wrong with Dr. Mike's observation. You're just saying that those two are more closer, the discrepancies closer to the globe than flat Earth, but you're not saying that there's something wrong with the observation itself.
No, no. From what I've seen, his observations as far as timing in general have been pretty good. There's some questions obviously about Green Mountain and Greenhorn Mountain, and there was some questions about the first release set of Blodgett Peak data that he didn't video, but from all the ones that he videoed, other than the Green Mountain
So
and Greenhorn,
39 out of 39 observations are tight then.
no.
Okay, what are you saying, Jesse?
Within a peak group, like all the measurements taken at Blodgett Peak, for example, they all agree with each other pretty closely from what I can tell. I picked the first two,
All right.
and they agreed with each other pretty closely. I assume the rest would. I know
Does the
the
timing match what was predicted for flat Earth?
no.
No, it doesn't. What are you
Well,
talking about?
there's always nothing matches perfectly. The question is which is it closer to? In the case of Cheyenne, am I saying Cheyenne right? I don't know how to pronounce them Indian words. In the case of Cheyenne, of the first two samples, one was closer to the globe and one was closer to flat, but they were both right near the middle point.
So when me and Alan went and tried and verified all of these timings in Stellarium, there was about a plus or minus 1 arc minute. So I mean, they're pretty solid, which means the timing's matched, which means you can have a prediction.
Plus or minus 1 arc minute from the average of that peak group, or from the flat Earth prediction?
No, I'm saying like each individual observation we verified.
Against what?
No one's talking about the average peak. Like, why are you trying to make it an average or a mean? We're talking about individual observations here, and they are all within plus or minus 1 arc minute. So what I'm just trying to figure out, what is your contention? So you're not contending the actual observations. You're agreeing with the observations and the timing. You're saying that these are actual timings. They match up.
They're the timings that Dr. Heverin gave us. It's all I've got of.
And then did you verify those timings and they match up, like me and Alan did?
Well, I'm not anywhere near Colorado, so I didn't actually go remeasure them myself, but I went and put them into Stellarium, if that's what you mean.
That's what I mean. Yeah.
I did. Yep, I did.
And they match up. The timings. Yes.
Mount Rosa is much closer to flat Earth than globe Earth, but not Blodgett Peak or Cheyenne. Those are both about in the middle. Well, actually, Blodgett Peak is closer to globe Earth, and Cheyenne is right in the middle.
They're all flat Earth, bro.
Well, how do you figure? If I use the method, and
because they match up with the timings that were observed.
Well, how did you get the height, Jesse? Maybe that's the problem. There's some discrepancy in the methodology here to give y'all different times.
I looked it on Google Earth and I checked it in the claimed height in his spreadsheet.
Oh, do not use Google Earth. How did Dr. Mike get them?
Yeah, Taylor, just relax.
What?
The height's fine.
Google Earth, it's fine, right?
Well, he got them two ways. He used the official height, which is going to be just the Google Earth height. He said he got it from the city's official height data for that mountain. So that's just the GIS data. That's what Google Earth runs on, is the GIS data, the digital elevation model. The other height he got had to do with using his method to measure the heights of the mountains or something like that.
Do you agree with the heights that were put forth? That's all that matters.
Yeah, so real quick, just to touch on the elevation differences, I had our boy Eric check the difference from the ECI to ECF coordinates or whatever, and versus what, Mike
40
did for
feet difference, right?
Mike did for his. No, it wasn't even that. I don't even remember it being that much.
I think it was like either 40 or 4. It was pretty close.
I'm pretty sure it was like the same. So anyway, yeah, the height and elevations are solid.
Yeah, I don't understand Jesse's contention. So, I mean, you're saying that they matched up in Stellarium, which means they match a flat Earth prediction for all 39, but 2 of them, you say the discrepancy matches more closely to the globe than flat Earth, but that doesn't even make sense because if the timings match up to what was proposed, then it doesn't matter with those 2.
Hey, Beasticles, would you be able to actually describe the process, the input data and the resulting data of this method, of the Heffron method? It sounds to me like you don't even understand the method or what it is supposed to give.
It sounds to me like he was asking you to explain and clarify your contention because it didn't make sense.
Yeah, I'm
No.
still trying to understand your contention.
Well, let's go over it, Beasticles, because you seem to be missing the point here. The first step is wait for a
That's
star.
not what he asked.
Okay.
Yeah, you're straight.
mean-
well, hold on. Like, you're straight gaslighting him now. Like, that's crazy, dude. Why don't you
Well,
just? Well, he's asking you a specific point of contention,
what's the
right? Because
contention?
the timing is what creates the difference here, right? And the timings all match, which you agreed, and so he's saying, "What is your problem?" And you're like, "Well, when I do a group analysis of it, it's blah blah blah, right?" But individually, each one of these matches. That's what the whole point of this is.
Yeah. Within
So,
one
maybe-
plus or minus 1 arc minute, like that's
I might see the misunderstanding. When I say that the timings are all about similar, I'm talking about compared to each other within, say, the Blodgett peak group. In other words, the readings are consistent with, each other. There's not wild variation among the readings. I'm not saying that they match the flat Earth prediction. I'm saying that at least they're consistent with each other in that group. Does that make sense?
Jesse, what happened is he got the elevation heights different than Dr. Mike, and that's where the discrepancy is coming in. That's what just saying it's one thing, and you guys are saying it's another. So maybe Jesse, you can show us how you got those elevations.
Are my elevations wrong, Alan?
it gives the same angle for all the other mountains that we have. So it seems to be the exact same thing that we're using.
That's what I thought.
So where's the
Who knows? But we seem to be kind of lost in a circle here.
Yeah, I don't understand Jesse's contention.
Well, would you like to?
Yeah, what's your contention for the
Okay.
5th time?
My contention is that a method has been given and sample data has been given, that is dates, times, and a location of the mountain peak. And the method given is said to be able to take in those input variables, the date, time, and elevation peak location, or the peak location, and give the true geometrical, the true physical elevation angle to a mountain peak. I'm using the sample data. No, did that not make sense?
Yeah, that's what he's trying to do is, create a straight line, force a line from observer to mountain peak to star. Go on.
So did I describe that correctly?
So what's the contention?
Well, if Beasticles doesn't think I described it correctly, then either I'm wrong or he doesn't understand it, or I just didn't describe it clearly. So we need to get. Did I describe it correctly?
Just keep continuing your, like, what is your contention exactly? You said the method, the given method. Continue.
Well, the given method is claimed to be able to take those input variables and produce an output, which is the true geometric physical angle to the top of that mountain, right?
Okay.
Mm-hmm.
With you so far?
Good. So I followed the method using the sample data given, collected by Dr. Heffron himself, and it gave me an elevation angle, and I compared that to both the globe predicted elevation angle to the top of that mountain and the flat Earth predicted elevation angle to the top of that mountain. Blodgett Peak matched the globe more closely by quite a bit, and Cheyenne was right between, about equidistant between flat and globe prediction. That's my contention.
Now, what about the other observations? Let's go back.
Wait. Hold on. Wait. In what way did it match a globular prediction more than a flat baseline? It matches perfectly the expected angle using plane trig and drawing a triangle.
Can I say hi real quick? I haven't been in and I've long.
Absolutely not. Please continue, Piezo and Bessie.
Yeah, like it matches a triangle, a trigonometry, plane trig, flat baseline angle to the peak, which is just the flat baseline that we believe in. So, like, why? What do you mean it doesn't fit that?
Well, it doesn't match exactly, and nobody expects anything to match exactly. It matches within, well, for example, Blodgett Peak. Sorry about that. My thumb slipped off the push to talk button while I was scrolling. Hold on just a second.
Yeah, it was within plus or minus 1 arc minute for just about every location. In fact, I think less than that in most cases because his footage for the time lapse was within plus or minus 1 second of the frames, and so that's like a quarter of an arc minute. But by the time most of the calculations are done without the arc seconds on there, so that's where the plus or minus 1 arc minute comes in. If you count the arc seconds, then it's probably within some precision within 1 arc minute off that. But without counting the arc seconds, it was pretty much spot on.
Well, so for example, on Blodgett Peak to LP Aquarii, and this is using Dr. Heffron's results from Stellarium, which favor the flat Earth. The difference between the altitude angle given by his Stellarium and the plane trig flat Earth prediction was 5.2 arc minutes. It was 5.2 arc minutes below the flat Earth trig prediction. That's not exactly on. It's close. It's within 5.2 arc minutes, but it's not exactly on. And I wouldn't be whining, except it's only 4.5 arc minutes from the globe prediction, so it's closer to the globe prediction. And that's the problem. When the noise is greater than the signal, or when the results aren't consistent one way or the other, then how can we depend on it? That's my contention.
Alan, did you get 5.2 arc minutes as well?
I have to go back and look.
Yeah, you should definitely do that.
Okay.
But all the other observations are cool, right, Jesse?
I doubt it. I checked.
What do you mean you doubt it?
Well, I checked 2 of each of the 7 locations, and they're not all cool. So
I was muted. I'm sorry. It says right here it's 41.4. The flat delta altitude is 41.4, and the globe delta altitude is 59.8 for LP Aquarii at Blodgett Peak on February 7th. 41 is a smaller number than 59.
Yep.
So what is the correct elevation angle for that one? Using the Heffron method?
The elevation angle was 112.
Yep. And 7 arc seconds.
Okay. Now convert that to degrees, or convert that to arc minutes.
72 arc minutes.
Okay. No, is that okay? Yeah, 72 arc minutes.
Yeah.
Now
60 plus
calculate
12, right? Yeah.
60. Well, don't forget the 7.3 arc minutes. But
Arc
anyway,
seconds.
or seconds, yeah. Now take and calculate the flat Earth predicted angle and convert that to arc minutes.
Yeah, 1 second. So you got distance is 35,910 and official altitude is 2870. 1 sec. So let me put, sorry, I gotta put this in Wolfram Alpha because I don't have my calculator and it's in another room. So that ends up being arctan of what's the distance? 2,870 over 35,910, I believe.
Yep.
Yeah, 1 sec. That is point zero. Hold on. 4 arc minutes and 47 arc seconds. No, I'm using degrees. I need to change to radians. Hold on. I'm not getting Wolfram Alpha is giving me all kinds of crazy numbers. I need to go get my actual calculator. I'll be back.
By the way, you can also use Google. You can be like, say, arctan, opening parenthesis, 500 feet slash for divided by, 30 miles, ending parenthesis, in degrees or in arc seconds, and it'll just do it for you. It converts all the units for you. It's pretty handy. You still there, Alan?
Yep.
If you look at the bottom of my chart, just before the last two, you'll see my 4 planned sightings. I have to wait till the snow melts, but
I've seen that. Looking forward to those.
one of those is at 7.2 miles. And if Stellarium's predicted occlusion time is anywhere close, the Heffron angle will be almost negative 20 arc minutes for a peak that is the same height as myself, the same elevation as myself.
I got 1 degree and 16 arc minutes for Blodgett Peak, based on the official altitude minus the observer altitude.
Got 117.
Something's wrong. If you got more than a degree of difference.
1 degree, 16 arc minutes is the
difference?
predicted angle. No, not difference. Is the predicted angle.
Oh, okay. All right, so that's 60 plus 16, right? So 77.
60 plus 16, 76.
Oh yeah.
It looks like he said elevation angle measured was 112. Based on the, is this the timing based elevation angle?
Yeah, the Heffron method is using his method of putting stellarium on the mountain peak with refraction turned off. So I bet if you subtract those, it's around 5 arc minutes. 5.2 is what I got.
It's just under 4. It's like 3.9 something degrees. Arc minutes, arc minutes.
What's your flat Earth predicted angle again?
1.6. Hold on, let me go back.
112.
No, from plane trig.
117 or 116.
It is 116 and 5 arc seconds, and he got 112 and 7 arc seconds. So it's 3 arc minutes and 58 arc seconds.
What?
So just under 4 arc minutes difference.
What are you using for your? Let's see. What are you using for your flat Earth prediction exactly?
I'm using the arctan of official altitude minus observer altitude over distance.
Okay, and what is that delta that you're using?
What do you mean?
It comes out to 800, Jesse.
800 meters?
Yeah.
Just under 800. It's 794.92, I think.
Oh, I'm using 807 meters for the delta altitude.
Yeah, 2870 minus 2075.08 is 794.92.
Let's see. So, what's the official altitude of Blodgett Peak?
2870.
Well, yeah, 2870 on the spreadsheet. I'll look it up, verify.
Yeah, so basically,
yeah,
using his method, he's giving what he calculated the actual altitude of the mountain to be. That's how he did this spreadsheet. The other spreadsheet he did differently. He did it with instead of giving it in terms of average altitude, he gave it in terms of the average angle, didn't he? Wasn't there another one before this? This is the most recent one, right?
Yeah, the other
Yeah.
one before.
Yeah, so we're looking at just under 4 arc minutes. But you can round up and say 4 arc minutes difference between the quote unquote official altitude and what he measured.
Let's see. the official altitude is 9,430 feet, right?
I don't know. This is just meters.
Yeah, I went to the Wikipedia. It gives 2,870 meters.
Okay, I found like what did I find? I found 2878 to be the highest peak using Google Earth, it looks like.
I was reading a paper about how Google Earth like is more inaccurate in like any sort of rough terrain. Like
Well, Google Earth doesn't give a precise. Just so you know, I've had to do this for school. When you use the elevation surveying tool on Google Earth, it gives like an estimate within the nearest. I think it tries to give it within the nearest 5 meters most of the time, but like it's not always. It's not always accurate.
Especially if you click wrong.
Well, yeah, it also doesn't have like extreme precision, like clicking here versus there, like right next to two little places right next
2
to each other with the
pixels.
mouse.
Yeah. Yeah.
Yeah, it's not like that.
That's what Eric was saying.
Why you just use like we have. I mean, we basically have to go off survey data unless we want to go do some kind of crazy surveying ourselves. But we didn't. We'd still be using like a datum line in order to get our mean sea level elevation. So ultimately, if we're going to use Tolera, we might as well use their survey tool altitudes as well.
Okay, I put in the higher official value of, well, it's in feet. Hold on. $2,874 meters. And that moved them a little bit to the flatter side, but they're still about equidistant.
Yeah, I mean, if you use the 28, if you add 4 meters to it, it becomes 1 degree, 16 arc minutes, and 26 arc seconds. So then it's off by about 4 arc minutes and 21 arc seconds.
And what's it off by the from the globe?
Hold on, I don't know. I gotta check.
59.8.
Yeah, I get 4.9 and 4.6 off from the globe.
You're talking about in terms of arc minutes. He's talking about in terms of meters. Like so, like on the spreadsheet, he has it in terms of meters, like the delta. Right. So.
Yeah, I'm talking about elevation angle in arc minutes.
Yeah, I know, but on his spreadsheet, he has it converted already to from a degree measurement, arc minutes, into raw meters. So these columns where he has the delta altitude, flat versus globe delta altitude, the flat delta altitude is negative 41 meters, and the globe delta altitude is positive 59 meters. So the flat is 18.4 meters closer, or lower of a delta, rather.
That's what I was trying to understand your contention earlier, Jesse, because I'm looking at the same spreadsheet. I don't know how you got your numbers.
Well, look at the I'll post my spreadsheet and you can see. Look at the last two populated columns or rows. Especially over on the right where it says GE diff, arc minutes, and FE diff. By the way, just as a point of interest, if you take the angles derived by the Heffron method and calculate out the difference between it and the official mountain height, you get an error of like 160 feet of elevation.
Well, that's what we're talking about, bro. There's a 40.5 meter 40.5 meter altitude differential between the plane trig and what he measured. But there's a 60.7 meter differential between the globular and what he measured. So that's what these columns are on his sheet. He shows his measurement and then the delta between each baseline. And as I go, I'm looking at this sheet right now. Pretty much every single one of these is like FE's delta is much lower. I think actually every single one is lower. Yeah, I don't think there's a single one where it's not lower.
Except, does he show? But he shows some that are about equidistant, right?
I mean, are we looking at this? Are you looking at the spreadsheet? There's a green column and a red column.
I'm looking at my spreadsheet.
Okay, well, we're looking at his data. So
Here, I'll post it for you, Jesse, if you don't have it. Here you go.
I have it, but I don't need his calculations because he gave me his method. So I can use his method and compare it against Flat Earth and Globe Earth predicted myself.
Where are you going to get the data from?
I'm using his locations and times because he provided that, and then the rest I calculated. I use his data. I'm not using his conclusionary in his red column.
Okay, so basically what you did is you took his columns where he has the delta altitude and you just converted that to degrees, to arc minutes. Got it. Either way, it's the same difference. He gave it in terms of raw meters. You're giving it in terms of arc minutes.
By the way, could any of you bring up Stellarium and just spot check one of these Blodgett Peak ones?
Which one?
Alan, don't you have that?
Yep.
Yeah, I mean, me and Alan went through all of them.
Yeah, how about Blodgett Peak to HD 216718? It's the second one it's the second row for Blodgett Peak. I got different elevation angles from Stellarium than he did, given the same date and time, and I'm not sure why.
Oh, let's figure it out. I got you. HD 216718.
That's it.
What do you mean he got different angles? The angle that he's giving is the timing angle that he got. Right, not what the Stellarium says. The Stellarium is incorporated into the rightmost column where it says globe delta altitude, which is comparing what he got versus what it's supposed to be, and then converted into meters.
718. Yep.
Yeah, 216,718.
Okay. Oh, you got to turn off the crap.
I heard that.
What time and date?
The timing is 1906. Oh, 2725.
Yes, February 7th, and then 19/20/24.
Yeah. 24. Boom.
And then you got the lat long coordinates.
Yeah.
And then on the top left.
I can make it.
Oh, by the way, for all those interested, Dr. Heffron a lot of times would use two half quotes in place of a single quote when indicating
right there
arc seconds. So if you're pasting it into Stellarium and it's not taking it, just change that to an actual quote mark. And sometimes he used a backtick instead of a half quote for the minutes.
It's there somewhere.
Yeah, I
think it's in tools. Tools, yeah. I remember the struggle, bro.
There we go. So, 1 degree, 11 arc minutes.
I mean, that's pretty much within the range. What's wrong with that?
11 what? How many arc seconds?
So that's the raw angle to the star?
0.4.5 arc seconds.
Okay, that's what I got, but he reported 46.5 arc seconds.
That's wait, no, that's what he measured.
Yeah, that's what he. Yeah.
right? His elevation angle column is what he measured.
Using stellarium and timing, right?
No. Using what when the peak was occluded via his camera.
But
So remember, this is refraction turned off for the star. If you turn refraction on, this is going to jump up to like 120 something. What does it jump up to when you turn
126.
refraction on?
Yeah, the angles he
Oh.
gave are based off of timing. Comes up
Yeah,
to
131.
Oh, wow.
And that's a big refraction here.
That's crazy.
Yeah, 20 arc minutes. Yeah.
All right. So
So he's off by differential. That's 4.5 arc seconds, and he's 46.5 seconds. So he's off by 42 arc seconds. So less than an arc minute. So plus or minus, that's 2/3 of an arc minute, basically.
Right.
So that's within 1 arc minute, bro. That's what I said earlier.
Yeah, but that makes a significant difference. That 40 arc seconds makes it closer to the globe than to the flat Earth.
No, it doesn't. The globe should be 131.
What the ruck, bro? That.
Well, try it. Take the you said you got 1 degree 11 minutes and 4 arc seconds, right?
Yeah, it's right there on the screen. Are you watching Alan's stream?
Oh, I was, but I went back to here. Hold on. I went back to the text chat to get you guys the link to my spreadsheet. Okay, yep, that one.
Yes,
okay, so
111 and 4.5.
Okay, so that's not the number you tested against the flat Earth prediction earlier, right? You were doing 1146 and a half. So
no, that was showing you what it is with refraction turned on.
No, 146. He's talking about 111.46. That's what Dr. Mike got with his occlusion timing. Like the time that it was occluded corresponds to the elevation angle he gives on his sheet.
Right.
So he must have just bumped the time roller a bit or something. So let's take if you take this 1 degree 11 minutes and 4.5 arc seconds, and you subtract that from the flat Earth plane trig prediction, the difference is going to be greater than 5 arc minutes and less than 5 arc minutes difference from the globe prediction.
Hold on a second. Wait. Where on this spreadsheet are you getting his occlusion angle? What's his occlusion angle for this star that he measured?
1 degrees, 11 minutes, and 4.5 arc seconds, like Alan just had on his screen.
No, that's the stellarium predicted angle from on top of the mountain.
Right.
He physically took a telescope from 35 kilometers away, looked at the mountain, hooked a camera up to it, and measured what time the star disappeared.
Oh, you're asking what occlusion time I'm using? Oh, I can get you that. Hold on.
What?
Yeah, so like, are you even on the same planet as us right now?
Yeah, I'm using
in this conversation.
I'm using 2/7/25 at 19/20/24 UTC minus 700. Obviously, I got that in right because I got the same 1 degree 11 minutes and 4 whatever it was 4.5 arc seconds that he did or that you did that Alan just did. So I got the timing correct. I got the location correct. Otherwise, I wouldn't have gotten the same elevation or the same altitude angle from stellarium, right?
Okay, so what he measured was, or sorry, where he was, the flat baseline, right? The flat baseline was 116 and 26.
You should share your
And
screen, Piezo. You can show this little Microsoft Paint.
Yeah, do you want
hold
to
on
do a
one
little
second.
MS Paint or what? Is there a doctor in the building?
No, hold on.
Yeah, 116.54. Almost
Nice.
17.
Let's go. All right. Let's all pop into Piezo's stream.
So depending on which number we use, if we use 2870 or 2874 for the height of the mountain, it'll change it ever so slightly. But I used 9430 converted to meters because Blodgett Peak right here, it says is 9430 highest point. So 9430 feet to meters is 2874. So I used the arctan of 2874 minus 2075.08. That's how far away he is from the mountain. Over, or sorry,
Hold on just a second.
That's the difference in
so the
elevation.
altitude, yeah, the elevation
okay.
difference. I'm sorry, that's the elevation difference over how far away he is. Yeah, which is this. That gives me this number, which is 1 degree, 16 arc minutes, 26.4 arc seconds.
Take that, subtract from his actual
Yeah, and then if you look at the spreadsheet is
111, 46.5.
46. So I'm guessing, right, I'm guessing this differential between 111.46 and 111. What did you get in Stellarium, Alan?
04, 111.04, something like that.
111.04. Okay. So it's like a 42 arc second difference, which is about 3. It's 4 seconds per arc minute, right? So it's like 3 seconds of timing, basically. So it's like a 3-second difference. So, anyways, if we can use 111.04. If we use 111.04, then we're 5 arc minutes and 22 arc seconds different. Okay.
All right. And is that closer to globe or closer to flat?
Let's see. You got 69 miles per degree divided by 60 arc minutes. Let me change it. How many 69 miles to kilometers? 111 kilometers. Okay. And I'm going to take 111 divided by 60. So you've got 1.85 kilometers. So 1,850 meters per arc minute divided by arc second. So you got, no, that's not how we do it. Actually, I know what we do. We just use a trig function. We take one angle and the other angle. So we do arctan of we do the 39,000. What was the number? 35,910. 35,910. Hold on, I got it. 35,910 times the tangent of 1.274 degrees. Okay, so that's 798 meters. And then we can
So we'll keep that in mind. And let's do the
so
globe
that's
math.
now 111, right? 111, let's see, 11 divided 11 and 4 arc seconds. So 4 over 60 is 0.067. So, and then 11 over 60 is 0.183. 0.183 and 0.067 is 0.25. I don't know. 11.067 divided by 60.1845. Yeah, so 1.1845 degrees, right? Yeah.
No.
Yeah, that's 111. 1.184.
That's not the globe prediction I'm getting.
That's 1 minute, or sorry, 1 degree, 11 arc minutes, and 4 arc seconds converted into degrees. I can
I
even
don't.
use this to check it. Here, I'll use Wolfram Alpha. Here, I'll use 1 degree. Whoa, why is it not working? That's so weird.
Whoa.
1 degree, 11 arc minutes, 4.5 arc seconds to degrees.
Seems to be
Hold on.
1.8, 1.185.
Yeah,
right there.
yeah, 1.185. Yeah, that's what I got. So yep. So that we take the tangent of that.
Is that radiant? What?
And we take 35,910. So we pop this into 742. So now we've got 798 minus 742.
And that's how he got his green column.
798 minus 742. 56 meters.
Hey, that looks like
difference.
it's about the same on the red column. 56.2 right there. Huh.
What was your predicted globe angle?
Was it 1.18?
It was 111 and 4 arc seconds. So look, the globe differential right here is 56 meters. His spreadsheet says 56.2. So that's just in terms of how many decimal places we used when we counted this. That 0.2 is just decimals.
Okay, so my globe prediction is 1.12 degrees. So we need to figure out whose globe prediction is wrong here, because they don't agree.
Okay, what's the globe angle? 111.04.
The globe angle that I get.
Alan just pulled it up on Stellarium.
No,
we just all watched it.
No, I mean doing trig on based on the observer location and the target location and the angle and the 8 inches per mile squared.
No, we want the angle from the mountaintop.
No. If we're gonna be comparing.
All right.
Hold
this
on.
is a giant waste of time.
If we're gonna be comparing the Heffron angle to a plane trig prediction for flat Earth, we need to also compare the Heffron angle to a plane trig prediction for the globe Earth. You see what I'm saying?
A plane trig prediction for the globe. What does that even mean? Is the globe a plane?
That means.
He means calculation.
Well, no. When we're doing this plane trig, the plane is up on its side because we're doing a right triangle. It means we take the flat Earth prediction and we subtract 8 inches per mile squared.
And Piezo, this will be good for everybody. I think we should do the correct angle. So, where are you getting your angle from, Jesse? If it's not 111.04.
Very simple. I take the arc tangent of the rise over the run, just like I do for the flat Earth predicted trig angle. Then I find out what the drop from the horizontal would be due to 8 inches per mile squared, and I subtract that from that. That would be the physical true angle to that mountaintop on a globe.
Yeah, so...
Hold on, I got company.
Yeah, that's what I used, 1.274. Tangent of that angle, we got the angle. This is rise over run. Here's the angle, right? This is it converted to degrees. We take that times the baseline distance, and we get the height. 798.
Oh, no way.
Okay.
He's deafened, by the way.
I'm back.
Oh,
Welcome
there
Jesse,
he is.
I already did that. If you were watching anything that happened, you are literally going in a circle and wasting time. I'm finding it hard to believe you're not doing it on purpose, but we'll look at this one more time. If you can see my stream, are you watching my stream? Did you watch any of it?
I've been watching it. I only had to go real quick because somebody knocked on my door, but I got rid of them real quick.
No, that's not what I meant. So you said rise over run, the arctan, right? That gives us this. Okay, that gives us this 1.274 degrees. So I take.
Do you agree with that, Jesse? Real quick.
Well,
let's just go step by step.
Well, subtract 8 inches per mile squared from the rise.
Dude, we've got the height of the mountain, the height of the observer. the difference between those two, that is the vertical arm of the triangle over the horizontal arm of the triangle. And we take the arc tangent of that, and it gives us this.
Okay, hold on. Let me check that against what I have. I'm not trying to do anything bad here. I just want our stuff to agree. You know, we're doing the same math. It should agree.
Okay, well, I pulled this straight off the spreadsheet as everyone watched.
Yeah.
Okay, I get 1.2815. And you're getting 1.27.
Jesse, did you take the height of the mountain minus the height of the observer?
Yes.
Okay, did you divide that by the distance away from the mountain?
Yes.
Did you take the arc tangent of that value?
Yes. Obviously.
This is the answer.
You must be. What height are you using?
I just showed you.
2874.
2874. Just like you.
2874. Let me convert that to feet and put that in my spreadsheet.
That's 9430.
All right, 2874.
As monotonous as this may seem to most people in here, I think it's good to see what's going on. I want to see your contention, Jesse, and give you a fair shot. And Piezo, thank you, bro. You're showing, like, I need to see the visuals for this too.
Okay.
All right, so what's the observer height again?
2075 meters.
All right, let me convert that.
Okay. Well, I'm not doing any converting. I'm just leaving it raw in meters, so there's conversion's not necessary.
Well, he's doing it for his spreadsheet because you have it in feet, right, Jesse?
Right, I got it all in feet.
Okay.
Imperial units suck when we talk about math.
Hey, Celestial Theodolite week 3, baby. Let's go. Apparently, Jesse's got a contention, so let's see.
Okay,
Did you get any different numbers, Jesse?
Yeah, my observer elevation was off 5 feet, I guess. It was different by 5 feet. So now I have 1.2752274. Oh, what's your distance you're using?
35,910 meters.
Okay, I'm using the exactly calculated based on the distance between the latitude and longitude of the 2 points. But let me plug this in.
What?
Yeah, my spreadsheet automatically takes the coordinates of the observer and the coordinates of the target point and automatically calculates the miles.
Yeah, well, he has already given us the distances.
Well, I need everything to add up, you know. I don't just take someone's word for something. I like to test it.
Gotcha.
All right.
Yeah, it looks like it's a difference of a hundredth of a mile or something.
All right.
All right, now I got 1.2744. So that would
There
round
you
down.
go. All right.
All right. So once you take that number, okay, the tangent of that number, right, multiplied by the baseline, and it gives us the altitude. Okay.
In meters. Yeah.
In meters. I mean, his is in feet, but we did it in meters. So I'm just showing you because his spreadsheet's in meters. So we're going to compare this to his spreadsheet, right?
Right.
So
okay. So now our flat Earth predictions match each other now. Now we need to figure out how to make our globe Earth predictions match them, right?
So what would be the difference in formulae versus
It,
arctan? Is it arc sine over the radius of Earth
No,
or
no,
something
no.
like that? No.
He, oh, what you're talking about something different. I thought you were about to ask about this.
No.
yeah,
No,
I
I'm
will.
just saying. Go ahead.
Yeah, so you need to subtract the Earth curve drop of 8 inches per mile squared or whatever from the rise.
Okay. Let's see if we can figure that out, Pieza. All right.
It looks like 332 feet of drop. Oh, I'm sorry. You need that in meters. Hold on.
Hold on
56
a
point.
second, real quick. What were you saying you're doing? I'm sorry, I was blanking out because I was doing this.
You subtract the Earth curve drop from the rise number, and the Earth curve drop
Yeah.
is 101.2 meters.
Okay.
Okay. What's the formula for drop over distance in meters? Because I don't know it. I guess I could convert it into miles and do that, but hold on.
You're making Wolfram Alpha work today.
Oh, that's true.
By the way, I really appreciate this, guys. I really do. I know it's
Yeah,
the
dude.
last thing you wanted to do, but I appreciate it.
Nah, dude, you got a contention. We'll address it. If it's a real contention, well, you know what I mean? Be fair. Okay. There you go.
331.92 feet.
Yep.
Right. Okay.
That's what Earth curve calculator said too.
And then so
Okay,
you're
so I'm going to
saying
convert that to meters.
right, convert it to meters first, right?
Yep, which will be 101.2.
Yeah. No, well,
Well, if you round it to
okay.
1.
Yeah, 101.2. It rounds up. Okay.
And then what? What were you going to say?
All right, so
And
subtract that from the rise. It's rise over run, but subtract that from the rise.
Okay, 1 second.
I think it's that one. Yeah, so 7.
Or add it to the, let's see, add it to the observer. You can also add it to the observer height if you want.
Okay, I subtracted it from the rise. So this is the meters of rise now.
Perfect.
Okay.
Okay.
Now that's your globe rise. So now just
Okay.
get the arctan of the rise over the run and give it in degrees. We'll see if it matches my spreadsheet.
It's looking like 1 degree 6 arc minutes, man.
Okay, 1.11301 is what I got. Okay, good. Now that we have the globe prediction and the flat Earth prediction, and you looked up and you got the 1 degree 11 minutes and 4.5 arc seconds, does that 1 degree 11 minutes and 4.5 arc seconds, is that closer to globe or closer to flat prediction?
1 second. Okay. 1 second. I'll open a new tab.
Then, so that's where he got his from in his spreadsheet.
We got 4 arc minutes and 17.7 arc seconds.
From the globe, right?
Yeah.
And 5 something from flat Earth, right?
521.9.
Right. So it is
based
closer.
on the stellarium position. Yeah.
Right. So that one is closer to the globe.
Okay.
Just barely, but it's closer. And that is the essence of my contention. And I think if you were to do the other Blodgett Peak ones, I know at least one of them would be in a very similar situation. And
You should probably do them then.
So
well,
one second. Let me see what happened with his math, because I originally got this number right here, right? And I subtracted this number right here.
Yeah.
Right.
And I gave you 56.2 or 50. Yeah.
Yeah. So what I'm wondering is, because 1.274, that's 116.26. That's the plane trig. That's the plane trig angle, right? Is
for flat,
116.
Yeah.
Yeah. So that's the bigger number, right? Bigger
Right.
number minus smaller number. Smaller number is stellarium number, right? That's because we got 1.1845.
Right.
Hold on.
Yep. 111.4. Yeah. That was it.
1.1845 degrees. Which is 111.4. Yeah, so that's the stellarium angle. Okay. And so then we subtracted those two. We subtracted stellarium angle from flat baseline angle, and we got a difference of 50. Hold on. Where was it? Oh, it was right here. 56.1 meters. And his spreadsheet says 56.2 meters.
Right.
That's the globe delta altitude, he said. So I'm wondering why he got that for globe delta altitude and not flat, because flat he got 45.1. 1 second. Let me see if I take Jesse's thing. 45.1. 1 second. So he got, because basically I just need to do this. 118.45.
We'll open another tab, bro. Let's go.
There we go.
You know, I think Second Opinion says he with the most tabs inherits the Earth.
$697.7. Oh wait, hold on. That's the wrong number. I'm supposed to be using the difference,
111.
which is this one.
Up top.
Yeah. What? Why is it not copying?
Just make that 111. 4.5.
Okay. Let me just type it. It's not working.
That's what I was saying too.
Okay, 44.8 meters.
That
What does
round.
his spreadsheet say?
45.1.
45.1. So then that's probably a precision, because this is 44.9, right? So 44.9 versus 45.1. That's just a rounding thing. So he's got these two columns on this chart that he has. So I'm wondering why the differential, because he got the same exact numbers as us, but they're swapped in places. So I'm wondering what this, how he's taking this differential of 45 or 56 and saying flat versus glob when it appears to be the opposite in this case, at least for this star. Because if we just take that distance, we take the, altitude. What's his average altitude? Oh, his average altitude is taking the angles he got via timing and comparing it to the official, right? Okay.
Yeah, we can't use that in the calculation because that was used to get the calculation.
No, that's the result, not the input.
Right.
And what's this right here? Oh, this is in terms of degrees. Okay. Wait a second. Wait a second. Okay, that's just in terms of degrees instead of arc minutes. Okay, I see what he did.
You
So
just
then,
separated it.
yeah. What's the d squared over 2r?
The d squared over 2r column identifies the obscured altitude, how much lower the peak should appear to be due to the alleged curvature of the globe Earth. The globe delta altitude indicates how much that deviates from the calculated altitude.
Oh, that's what we calculated when we did the.
That's at the top of the spreadsheet.
Yeah, that's the 8 inches per mile squared thing. Okay, got it. Okay.
So wait.
Okay.
Okay. So he's saying it should be 101 meters lower.
So his flat delta alt, so he says, identifies the deviation of the measured altitude from the official altitude. So basically if you take his occlusion timing, right? His occlusion timing corresponds to an angle of, what was it, 111, right? Okay. That 111 is like we're in stellarium, what we would see on top of the mountain with refraction off. You go and measure it compared to the flat baseline. The flat baseline's 116. You go and compare it to the globular baseline. The globular baseline's 106. And so I think that's why he says negative 45.1 and positive 56.2. So the delta, the flat delta, he says is negative 45.1. Because he measures a smaller angle. See, I feel like these columns are just flipped for this star. Like that's literally we got both these numbers within plus or minus 0.1 or 0.2 when we did it by hand. I kind of just want to ask Dr. Mike at this point.
Yeah, we'll have to.
I mean, I plugged this stuff in. I did it by hand.
Thank you.
Much appreciated, lads.
So, Jesse, real quick, other than those two discrepancies, what do you say about the other observations that show quite a big difference?
Well, you mean the other Blodgett
observations, the other stars, all of them,
the Blodgett Peak,
the rest of the stars, yeah.
Because it's rather laborious to key these all in from his spreadsheet, I just did the first two because that would give me an idea if they were similar. Both of the first two are very similar, and both
what
closer
about the Other
to globe.
ones. Yeah, I know about we've been talking about those two for the last hour now. I'm
Well, it's
talking
like
about what about the other ones? I want
it's
your
like
honest opinion on it.
You know, I'm wondering. Hold on a second. I'm wondering. You said that these were the only two.
I
So
did.
I'm curious if we were to do this for the entire sheet, right? If we were to do this for the entire sheet, if he simply, when plugging these values in, transposed these two columns for this particular star, and that's why this is the one that you asked us to look at, because this is one where he got it backwards and it's actually in favor of glob,
You
right?
know,
Because you said you plugged it all in yourself, right? But for
I,
on his sheet, it all looks favorable of not glob. So I'm wondering if this is one that got transposed, because you said the other ones that you looked at didn't favor. So we kind of need to plug all of this into an Excel spreadsheet, right, ourselves, and look at it. Because now the question is this a trend, or did he just pop these in the wrong column for this particular star, and you caught that because you already plugged it into your sheet, and that's why you're having us pick this one?
I honestly did not even try to understand all of his other columns and stuff. I understood his method of getting the time and the date and the peak location, putting that into Stellarium with the atmosphere turned off. You get an angle. That's your angle. I
Okay.
simply took his raw data, the timing, the star name. I just put them, the first two of each one of them, except two random ones from Pikes Peak. I just put them into my spreadsheet to kind of do a sanity check on on two from each of them.
Yeah, I think what happened is he used this elevation angle of 111.46, because once you add 46 arc seconds, it doubles the difference. So the actual overall difference becomes 92 arc seconds or 93, which is like 1.5 arc minutes. So it like this differential that we got, I think, is actually due to us using 111.04 and him using 111.46. Because if you use 111.46, you get his numbers, right? But we used 111.04, which is what we got in Stellarium. So, Alan, how precisely did you plug in the lat and long into Stellarium? Did you go all the way down to the arc seconds?
Ooh, so what I did is when you go down to the arc
Yeah.
seconds, Stellarium will auto round sometimes if it doesn't like what you put in, and that's what you get. So
Ooh,
so for Pikes Peak, right, we have, let me see
Blodgett.
here.
No, the one, the
Or
HD
yeah,
216718.
Blodgett. Fine. Yeah, 38, 57, 32. 38, 57, 32. Looks good on that one. 104.
Yeah, I remember
54,
Alan.
20.
Basically, if it was 59 or if
Yes.
it was
Yeah, so it took
1
off
degree.
it took off 1 arc second or half. Or
So, you got the exact lat long that's on his sheet in your Stellarium?
minus 0.01 arc seconds. Yeah.
0.01 arc seconds, not arc minutes, arc seconds.
Right.
Mhm,
Yeah.
correct.
Stellarium kind of, it won't let you set it to every increment of 100th of an arc second. It rounds it to like the nearby arc second. I don't know why, or nearby 100th of an arc second.
Right.
Okay. So
That's what it was doing to us.
it looks like the reason that we're getting the differential that we got is because our Stellarium angle that we got is different than the one that he's putting in here under elevation angle column. So if we look at his intro paragraph, it says EL column, elevation column, identifies the star's elevation at the time of occlusion. Okay. As from the mountain.
Here's what's odd though, is both LP Aquarii and HD 216718 were different by about the same 40-ish arc seconds.
42 arc seconds.
Yeah, from the flat Earth prediction.
From
Stellarium.
Stellarium.
From what you and I get in Stellarium, yeah.
I gotcha.
So I don't know, it's easy enough to bump the mouse scroll wheel when the mouse is over the time and date window and maybe bump it off a few seconds or something. But how did he get them both off the same amount or very very similar amount? I don't know.
Yeah, that's what I'm wondering, is because that's the cause for the discrepancy in the columns, right? Like is this elevation column right here, because we get 111.045 and he gets 111.46.5, which is a 42 arc second difference, which, because the deviation of the deltas is so small here, makes a difference. Some of these other measurements are like way further apart, like if you go down to Blue Mountain or Green Mountain or Mount Rosa or Greenhorn Mountain, especially, my goodness, like those are way further apart. But for Blodgett Peak, the numbers are way closer to each other. Now Pikes Peak, they're way further apart. Cheyenne Mountain, they're pretty close. Basically, all of them are really far apart except for Blodgett Peak and Cheyenne Mountain. So Blodgett Peak and Cheyenne Mountain, glob versus flat, is like within 1 arc minute of one another. It's plus or minus 1 arc minute, and those are like really, 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 really close. All the other mountains are like we're talking a difference of like hundreds of meters for each observation on the delta. So
Well,
I guess that was Peter's question to you, is like, okay, we've got Blodgett and Cheyenne, which you say there's a few stars that favor glob by about 1 arc minute, which is about 4 seconds of occlusion timing on the camera or whatever. But all these other ones
What
are
about
like
the other ones?
way further apart.
well, okay. So bear with me here. So the time and date, something's wrong with the time and date on Green Mountain and Greenhorn Mountain for the 4 samples that I took from them. For example, the according
So you don't want
to
to answer the question still.
No, he's telling us. Let him go ahead.
All right.
yeah. No, I looked at 2 samples from each target peak. Okay, and the vertical foot error difference between the first of the 2 mountains I mentioned just now was minus 4,000 feet and minus 1,000 feet. So that's a lot of, that's a huge margin of uncertainty there.
Wait, you
And,
saying the altitude he reported is wrong?
well, when I took the date and time that he claimed that star occluded, I got an elevation angle from an altitude angle from Stellarium that equated to the mountain being, in one case, 4,000 feet lower than the flat Earth trig prediction, and in the other case, 1,000 feet lower than the flat Earth prediction.
Because, yeah, so you're talking about Greenhorn Mountain? Because Greenhorn Mountain.
That's Green Mountain.
So let's do one more real quick before we close out. Let's do this Greenhorn Mountain. Alan, can you pull that up?
Your stream is paused.
Oh, okay. Alan, can you pull up Stellarium?
Sure can. 1 second.
Is everyone else having fun? I hope so.
Yeah, so we'll just use whatever this is. What is this?
I should
Greenhorn.
have a Greenhorn saved because I was just looking at it before live a little bit ago.
Yeah, do the first Greenhorn one. 28
Okay.
or 283.88.
280. That's Green Mountain, not Greenhorn.
I'm sorry,
Green Mountain.
Yeah, do Green Mountain.
Green Mountain. Here we go.
First one.
So
Let me see if the lat long matches.
Oh, yeah, okay.
HD2.
Yeah, it's off.
HD28388.
All right, 1 second.
Wait.
HD23.
No. 28388.
Gotcha.
But also the lat long are off.
All right.
Yeah.
What do we need on my lat long?
38, 41, 46.
8,
41, 46. And then 104, 57, 48.
Oh, weird. Why did it have it all messed up? Okay.
104, 57, 57. Yep, there you go.
Time now.
The time is 22:02:58.
What day?
March
The
1st.
the first, yep, March 1st.
If you're in UTC -7,
You got it on the 24th right now, bro.
I know I'm doing the time. What was the seconds for the time?
22:02:58.
Yep.
All right, and then the date was 2 what?
No,
March
3-1.
1st. 3-1.
Gotcha.
Yeah.
Okay. You make the text
Star.
big.
Yep.
It's in tools. Yep.
Nice. We've
Good old
become
Stellarium.
Stellarium professionals.
I see you
right.
struggle so much, bro.
All right, we're at
So-
0° or negative 16 arc minutes.
That can't be
Negative
right.
6.
Yeah, that's not what he wrote down, and that of course gives an absurd value. So there's some error somewhere.
1 second.
There, let's see, this was the before daylight savings time kicked in. No, after, right?
No, this is not the one that was messed up. This is new.
Yeah, so if you look
Try
at
an
his lap long,
hour. Yeah, try an hour before, real quick, Alan.
oh, is this the daylight savings time thing?
We're not sure,
Plus-
but we're checking.
Plus
No.
8 arc minutes, 16
Degrees,
arc
that's
seconds.
degrees.
Oh yeah,
That's
sorry.
what-
Yeah. Plus 8 degrees, 16 arc minutes.
That's
No, that's not it.
That's not it. This seems like another daylight savings thing.
Negative 10 an hour later.
Because I remember it being on the 7th. Or, yeah, the 7th was the daylight savings time. The thing is, are these dates wrong, though? Because didn't he observe Green Mountain after? Wasn't that like the latest one? He put
Put the
March
12th.
1st.
Put March 12th. Put March 12th.
I think that's what's going on here.
Negative
Go
7 degrees.
Go forward 1 hour. Go forward 1 hour. Go back 1 hour. No, that's not it either. Interesting.
I think it might have been. Oh, then he put. Okay, yeah, I think he just messed these up.
22:02:58. Yeah, we got that.
Because he put the date as
No,
March
change the
1st.
day. Just just go to 01 and change the day. Yeah. Keep going.
It would have to been after the 1st, though.
Yeah. Further forward we go. It goes negative angle, right? So you're all the
Alan.
way in April right now, bro. No, I was gonna say you can change the hour. You can go
I
back
think
1 hour for daylight savings time, and then change the date.
We're
and
gonna have to
see
talk to
what-
Dr. Mike about those, because then the other ones are also 3/16/26. It says, which I think is a mistake as well. But
Yeah, go to 16, and then change the hour to 21. All right, now count down the days. Start going down in the days one by one. Okay, go back up. 104. No, that's not what he got. He got 107 was his elevation angle. 107.00. Interesting.
I think he just probably copy pasted some wrong dates and times, because if you look at his column for what he got out of Stellarium, it's sane. But it's not what you get with these dates and times.
yeah, I think that's the case actually, because the dates. I don't think he meant to put March 1st.
Wait, don't we have video? Don't we have video, Alan?
Yeah, but matching it up with the timestamps and frames has been less than desirable.
No, frames is just seconds. You just count seconds. 6,682 seconds. Divide that by 60, and you got how many minutes?
Well, should have just asked you then. Okay, well, let's see. We got
It's
oh,
111 minutes and 22 seconds.
But besides that, I think you put the wrong. I don't think it's March 1st because these were ones he did
all right,
after.
all right,
for sure.
Piezo. We got a 17-minute, 28-second video. Tell me what timestamp to skip to.
Is this for what's this for?
This is Green Mountain.
It says Green Mountain 314. The date is 314.
314. Okay.
Yeah.
Well, that's the date we have on here.
Okay.
But what was the date that he put in his spreadsheet? Because that's what we need.
He put
for the time
he
or whatever.
put first.
He put the first, but it's the 14th on the video.
Yeah.
All right. So what time then?
So he probably missed the 4 when he stopped in 14, and Excel just corrected it to 1.
So you're saying that Green Mountain was the 14th?
Yeah.
Right. Correct.
He's got the date on it. He's got the date and time on the video title. He just
Nothing to my madness.
he finger fumbled the 4 when he was typing the date, and Excel just, since he only had a 1 in there, it just corrected it to the
So the
first.
time should be fine then. Go back
Yeah,
to
the
22.
time should be correct. Yeah, 22.
20, not 21.
42. No, 22:02 42.
22:02 58
58.
in the spreadsheet.
Oh, you're right. You're right. So this gives an angle of negative 8. Okay, now do the daylight savings time correction. 104.50. Okay, that's it.
There it is. Yeah.
Okay. So his spreadsheet says 107. Interesting. So let's run the numbers with 104.50. 104.51. Give me 1 second.
I'm on your screen now, Piezo.
So we got 104.51, and we've got a distance and a official altitude. Okay, so
That's better.
so there's our degree measurement. Now I need to use the spreadsheet. 1 second.
Yeah, that puts it within 74 feet of the flat Earth prediction.
Okay. Which is 17 meters, maybe? No, more than that a little bit, but
yeah,
20-something meters. All right. So let's do the math real quick.
For reference to those who are listening, that's 87 miles away.
This one's 32.75 miles away, right?
Oh, right. You're right. I was looking at Greenhorn Mountain.
Maybe we can figure it out next.
Yes.
52690. Yep.
Gonna go.
Okay, so this is the plane trig baseline. This is the stellarium angle. Okay, so let's see.
That's still pretty freaking close.
No, it's 1.5 arc minutes below the flat Earth prediction and 12.7 arc minutes above the globe Earth prediction.
One arc minute and 1.2 arc seconds.
That's pretty crazy.
Okay. Yeah, so he's within 1 arc minute of the plane trig baseline, flat baseline on that one. And
Yep.
then we got to do, what's the distance? 50. Hold on.
52,690.
Okay.
I got you, bro.
Okay.
32 miles. That matches.
All right, now hold on 1 second.
This is like a battle of math. It's like it's not as fancy. I'm watching Piezo spaz out here.
You're
There
doing
it
good
is.
work, Piezo. I appreciate this.
Okay, so the globe delta is 13 arc minutes and 11.4 arc seconds. Okay, so we got 1 arc minute and 1.2 arc seconds plane trig deviation or flat plane deviation, and 13 arc minutes, 11.4 arc seconds globular deviation. So this one's like way closer for the flat baseline. Now his spreadsheet has some elevation angles that are weird. I don't know why, like what is going on with his stellarium, but either way, using his timing data is all we really need, right? We just need the occlusion time.
Right, and that's what I did when I made my spreadsheet.
Okay. So it looks like the majority of these are going to be way closer to the FE, and maybe some of the ones on Blodgett and Cheyenne are going to be closer to globular for a few of these. So that's what it
So
looks like.
what I found in my research was that for mountains that were close, the Heffron angle would be below the FE prediction. As the mountain moves farther away, the FE prediction angle crosses the Heffron angle, and then as they get farther beyond that, then the Heffron angle gets higher and higher than the FE prediction angle, which is why the ones that are right around 30 miles an hour, 30 miles, 32 miles, 29.6 miles, those are all pretty close. The ones that are closer, like 22 miles, they are reading below the flat Earth prediction significantly.
You think that might have something more, instead of the distance, might have more to do with the actual angle as it compresses into the horizon, because those that are further away also have lower angles.
But anyway, could we
Yes.
I mean, look, the Heffron, I can tell you what the Heffron formula it is, but that would just derail us, and I'm glad to, but I would really like to see if we could get to the bottom of Greenhorn Mountain too.
Utility sync.
Well, it looks to me like,
Rusty worms.
as he gets
Weird crusties.
as he gets further and further away from the thing he's looking at, the angle to it gets lower and lower, right? And we know that based on the hyperbolic geometry of the way that we see Euclidean space, like the sky coming down, it curves off at the end in terms of miles per degree or whatever. It's not linear, so that compression effect might be one of the reasons why this is happening.
So are you saying the Heffron method only works for mountains around 30 miles away, but not for significantly closer or not for significantly farther?
No, I'm saying that when you see some kind of trend happen where you see this distance dependent effect, it's not actually a distance dependent effect, it's an angle dependent effect. And he said from the very beginning that angles that are closer to the horizon would see a more pronounced delta. Because the scaling isn't linear in terms of our visual space. When we see like the objects in the sky as they come down toward the horizon, all the information has to resolve to our eyes from a compressed horizon, and the closer to the horizon you are, the more compressed it is, and so it has a non-linear scaling component.
Well,
Some would say logarithmic.
It's like, yeah, I mean, it changes. It's like there's a linear portion, but it's like hyperbolic towards the end. It like trails off super hard.
could we take a look at the Greenhorn Mountain one?
I don't know. I gotta go. You guys can do that. I just wanted to drop in and see what was going on, but glad we could look at some of the math.
Thank
Yep.
you.
Thanks, Piezo. Much appreciated.
No
Yeah,
worries.
we'll
Thank you,
go through
Piezo.
the greenhorn real quick. We can get that done.
Hopefully that helped you guys understand the math some. Y'all have a good night.
Good night.
Later,
Later,
brother.
G.
Appreciate you. All right, Greenhorn Mountain,
Give me
which
all
has the most pronounced. I got you, bro.
give me all the necessary things to enter.
HD 35182. Oh, yeah, tools. Yeah,
Start with
cool.
HD 35.
35182. Boom. And we're looking at Laddie Long. Make sure that's correct on Greenhorn. We're looking at
Yeah.
30, 37, 52, 53. And then you got 105, 0, 48. And then we're looking at March 16th. What the fuck? Oh. 16th at, let's see, 20, 40, 25.
Onto the star. Can't.
Wait, you got to put on your
What's the star again?
HD 35 182. 35 182. No, that's 32.
Shit.
There it is, the second one. Second, yep. Yep. There you go. And then let's zoom in to that bad boy.
All right, we are at -4. What do we have to do? What was it? Back an hour.
There you go. Yep.
Do we have the right?
Nailed it. Nailed it.
Everything? Well, that was it then. It was just daylight savings time strikes again.
Daylight savings time strikes again.
And he had the wrong date on the one.
Yep.
And daylight savings time
I
struck there.
told y'all whenever
So
y'all.
my question is, why did it set 7 minutes roughly before or after Stellarium predicted that it would? Because Stellarium should be pretty good at predicting when the star is going to set, right?
What?
What? Looks like it got occluded at the corresponding time.
Within one arc minute. Yeah.
Yeah.
1 arc minute?
Within 1 arc minute.
What is the difference that you get between FE predicted and the Heffron method on that?
It's like quite a bit of difference there.
8 arc minutes?
I haven't done the conversion, man. This is in meters.
About 1,000 feet is what I get. Granted, it's much, much farther from the globe prediction. It's definitely closer to the flat Earth prediction.
Yeah. So.
But what would cause that error? 8 arc minutes is kind of a lot.
I mean, I don't know what you're asking. You're asking why does Stellarium have an 8 arc minute difference?
I don't. What are you saying? Did it not get occluded at the time that it was? Did it not match the prediction used?
I'm saying both things.
All right. Well, thanks everyone for joining.
Well, before that, any other questions, concerns from anybody else in the audience, just in case?
Does anybody else exclude me?
Well, I
Who's
mean,
you?
just because we've been going back and forth. I'm just
Yeah,
trying to get anybody else.
Yeah, trying to wrap up, dog. We've been going for 2 hours.
2 hours. Yeah, it was all right.
So we got over the major points of contention so far, which were anomalies in the columns there, which turned out to be dating errors. When we went back to examine the videos, the dating was off, and then obviously daylight savings time struck again. And there was, what was it, Blodgett Peak that matched the globe closer or whatever, I think is where we're at.
That was it. Yep. Nailed it.
Pretty solid update. Jesse, thank you very much. Much appreciated.
My pleasure. Thank you, sir.
Alrighty. Gentlemen, we are concluding this episode of Celestial Theodolite Part 3. Join us on Monday, next Monday, for Part 4.
All right.
Oh, and Geo, thank you very much for hosting. Shout out to Earth Awakenings. If you're not on Discord app and you're not on Earth Awakenings and or Ether Cause, probably not a very cool person. All I'll say about that. So here are the links to join. Absolutely not. All right. So that's the wrap up now.
Yeah, yes.